In this video, we talk about unconditional basis. Now, a basis in a Banach space is called unconditional if the series expansion of any vector into that basis converges unconditionally. Right, so remember that unconditional convergence means that you can change the coefficient by multiplying them by any choice of plus or minus 1 and the series still converge, or equivalently that you can sum the series up in whichever order you want and the convergence remains. Now, not every basis in a Banach space will be unconditional, and in fact, even in a Hilbert space where orthonormal bases are clearly unconditional, you can construct conditional bases, so bases that are not unconditional. Now, what does it mean to have a basis that is not unconditional? It means that you have some vector x that are such that if you multiply the coefficients by plus or minus 1, you start losing the convergence. And if the bases happen to be complete, for instance, because you're in a Hilbert space, or more generally speaking, in a reflexive Banach space, then you know that this can only happen because you get an explosion of the norm of the partial sums. And if that's the case, that really means that you can make the norm of a vector explode just by changing its coefficients by a factor plus or minus 1, by an appropriate choice of plus or minus 1. Now, what does that mean, really? It means that there is a diagonal operator which entries on the diagonal are just plus or minus 1. That is not a bounded linear map on your Banach space. So conditional bases are problematic because if you work with a conditional basis, even testing the boundedness of a diagonal operator will be difficult. Now, on the other hand, unconditional bases are great because we understand the boundedness of diagonal operator with respect to such basis. And that's really the content of Theorem 11.5. If I have an unconditional basis and I give myself a sequence of lambda n's that is bounded, sequence of real numbers, and I define a diagonal operator, let's define it to be sure it makes sense just on a finite linear combination of the EJs. You're just multiplying the coefficient by some lambda n's, and you ask yourself, is that operation bounded? Now, of course, it is bounded as it's defined here because I'm only acting on finitely many ENs, but is it bounded in a way that's independent of capital N, such that I have a unique continuous extension of T lambda to the entire space? Now, the answer is yes, if the basis is unconditional. If the basis is unconditional, there exists a constant such that for every choice of lambda n's, bounded lambda n's that I'm multiplying by, T lambda x, the norm of that will be controlled by a constant that doesn't depend on x or lambda, only the subnorm of the lambda and the norm of x. So this will mean that T lambda x tends to a bounded linear operator for any choice of lambda bounded sequence, so lambda in little n infinity, and with a norm as a bounded linear operator that only depends on the subnorm of the lambda n. So Theorem 11.5 is really telling us that with respect to an unconditional basis, we understand diagonal operators and when they are bounded. And as I was mentioning before, if the basis is not unconditional, then we really don't, because this property here can fail just for a choice of lambda n's equal to plus or minus 1. And that's why when we do spectral analysis and we are able to diagonalize or come close to diagonalizing an operator, we would really like it to happen in an unconditional basis. For instance, in an orthonormal basis if we're in a Hilbert space, or in an unconditional basis in a more general Banach space. Now, we're going to prove Theorem 11.5 in this video, but before we do that, we'll look at Lemma 11.4. Lemma 11.4 is really a special case of Theorem 11.5, where all the lambda n's are chosen to be 1 or 0, and they only one finitely many times. So, put in a different way, it is saying that if I take the coefficients in my series expansion of x into the basis of En, and I put 1 in front of finitely many of them inside a finite set J, and 0 in front of all of the others, I get a bounded linear map, Pj, which is really the projection onto those ENs that corresponds to an N in J, And the point is, these operators are bounded in a way that is independent of the size of j. In fact, you can take the supremum over any finite j of these things, and it's finite. So it generalizes the idea that the partial sums projection onto a basis are uniformly bounded, right? That's one of the assertions that are necessary for something to be a basis, necessary and sufficient. Okay, but what this is saying is that it's saying something much stronger. It's not just the partial sums, like up to the first element in the standard ordering of the natural numbers that are bounded, but the projections onto any finite set. And the fact that you have this extra ability to project on finite sets that are not just the first capital N elements when you deal with an unconditional basis kind of makes sense intuitively, because we know that we can reorder the natural numbers anyway when we have unconditionally converging series. So we'll prove this lemma first here, which in a sense is theorem 11.5 in the special case of a lambda equal 1 or 0 and taking the value 1 only finitely many times. And that kinds of come out almost straight away from this proposition 11.2 and what we understand about unconditional convergence. And then based on lemma 11.4 and the understanding of T lambdas for a very specific class of lambda, we'll get to the entire class of lambda in L infinity in the proof of theorem 11.5. So let's start with 11.4. Okay, so we'll prove 11.4 by contradiction. So we assume that the supremum over all j finite of the Pj norm as a bounded linear operator on X is infinite. Now that means I can have a whole sequence of jk's such that the norm of pjk's tend to infinity. But I want to do that in a nested sort of way. So let's see how we can ensure that this can be done in this way. I can pick a j1 in n that is finite, subset of n, and such that, let's say, the norm of pj1 is greater than 2. And now I'm claiming that if I look at the supremum of all j's that contain j1 and that are finite of the pj of bx, if I just only look at the finite sets that are bigger than j1, then this is still going to be infinite. And why is that? Let's prove this little claim. If this supremum here of pj dx, when j is included in j1, is finite, then we have the following. Okay, you give me any j finite, and I want to estimate the norm of pj. And what I can do, let's say on a vector x, I can rewrite this as the norm of pj union j1 of x. So I'm adding all of j1, so I'm not adding anything for those elements of j1 that are already in j, but I'm adding something for those elements of j1 that are not in j. So I should subtract the projection onto j1 intersected the complement of j of x. And that's an equality here. So, okay, but then I can use triangle inequality, and this is controlled by pj union j1 of x, plus one obvious bound that I could put on this projection here is just the sum for, what is it, for j in j1 of ej star tensor x, absolute value, times norm of ej. Now here I'm projecting onto a set that is finite, j union j1, and certainly contains j1. So this is smaller than the supremum of the norm of the pk, let's say, when k contains j1 and is finite, plus the sum for j in j1 of the norm of ej star times the norm of ej. Okay, and all of that times x. Okay, but what does that tell me? That tells me that the supremum of the pjx for all j finite is, well, is finite for all x. Okay, but then by uniform boundedness principle, this tells me that the supremum of the norm of Pj as bounded linear operators of a j finite has to be finite, and that's a contradiction. So we cannot have this, right? So if we can't have that, then we have the opposite. So, we cannot have this, so we do have that. So I can find a set J2 that contains J1 and such that Pj2 has norm, let's say, greater than 2. And then I can keep doing that. So what do we get? Well, we get inductively that there exists a family Jk of subsets of n that is such that Jk is always included in Jk plus 1 for all k in n. That was the point of that first claim, to show that we can construct this sequence in a nested way, and Pjk is greater than 2 to the k for all k in n. We constructed the first one to have norm greater than 2, and then we constructed a bigger set on which the projection has norm greater than 4, and then we can keep constructing like that, because the supremum of an old finite set that contains all of the previous one is still going to be infinite. Now I have this nested sequence of finite set jk. I can look at the union of all the jk, k equals 0 to infinity, and this can be described by a sequence of natural numbers, because you just pick all of the natural numbers that appear in J1, and then you add to that all of the ones that were in J2 but not in J1, and then you add to that all the ones that were in J3 but not in the previous one, and so on and so forth. So in doing that, you're defining a increasing sequence of natural numbers. So for some nj, a sequence of natural number that is increasing. Okay, but I have unconditional convergence of series expansion into the basis. So by unconditionality, I have that the sum of x e star nj e nj converges. Right? That's unconditional convergence thanks to this property 2, I think, of the proposition describing all the equivalent way of obtaining unconditional convergence, and that's for every x in x. Now, what is that telling me? Well, the pjk's are really partial sums of that series expansion here, right? The pjk is a projection onto the first few elements of that sequence, because the jk's are, because of the way that sequence was constructed, and because the jk's are nested. So the limit of the pjk of x, and it's a limit of partial sum of this sequence. The limit of that, as k goes to infinity, is the full sum j equals 0 to infinity of x star is, sorry, not x star, x en star nj enj, which we know exist because we have an unconditionally converging series. So this limit exists, but if some family like this has a limit, then in particular the corresponding sequence has to be bounded. So the supremum of a k of the pjkx has to be finite for every x in x. And now the uniform boundedness principle concludes the proof and tells us that the supremum of the norm of pjk's as bounded operator in x has to be finite, and that is a contradiction because we've constructed them such that they have norm greater than 2 to the k. And that concludes the proof of this little lemma. So let's prove theorem 11.5. So to do that, we're going to do a few reductions to bring the general case of a lambda in L infinity down to the case of just lambdas equal plus or minus 1, lambda n's equal plus or minus 1. So the first thing is that we remark that without loss of generality, we can assume that the subnorm of the lambda is smaller than 1. If not, you just divide by all the coefficients by the subnorm of the lambda and use linearity of the map till lambda. Now, the next thing we're going to do is we're going to replace lambda, which is a sequence which can take uncountably many different values, by a sequence that is close enough to lambda, and we'll see quantitatively what close enough means later on, but takes only finitely many values. So let's give ourselves a epsilon, and then we can pick a number d in n, and we can pick a sequence, let's call that L running between 1 and d, such that A1 is -1, AD, maybe AD plus 1 is 1, and AL plus 1 minus AL is smaller than epsilon for all L equal 1 to D. So we just partition the interval -1, 1, the intervals of possible values of lambda n, into smaller intervals of side lengths at most epsilon, and we have a certain number d of them that depends on epsilon. Okay, so now we're going to define AL for all L equal 1 to D, actually 1 to D minus 1, AL to be the set of all those n, such that, well, such that lambda n is in an interval AL to AL plus 1. And let's make it open on the AL plus 1 side, and then we define AD to be the set of all those n, such that lambda n is between AD and AD plus 1, which is 1. And then we close the interval here. So, okay, so we have that, of course, the union L equal 1 to D of the AL is equal to all of n, and for every n in n, there exists a unique L in 1D such that n belongs to AL. And we have a partition of n in that way, just looking at where our lambda n end up in this covering of -1, 1. Okay, so now we're going to define mu n for all n to be the sum from L equal 1 to D of the indicator function of AL of n. So we just pick that value of n for which n is in AL. And then we replace lambda n on that by AL. So whenever lambda n is between AL and AL plus 1, we replace lambda n by AL, and that gives us mu n, which is such that, so remark, mu n minus lambda n is smaller than epsilon for all n, because lambda n is always close to AL up to epsilon when n is in capital AL. So this is close enough to lambda n, but in the meantime, this only takes finitely many values, which are the ALs. Now, I want to show that the ALs can be rewritten as a linear combination of just plus or minus 1. So that is the next remark. Okay, so let's start with the following remark. If I have a number a, which is between -1 and 1, like one of my AL, I can always rewrite it as, well, 1 plus a over 2 times 1 plus 1 minus a over 2 times -1. So, and notice that 1 plus a over 2 plus 1 minus a over 2 is equal to 1. So any number between -1 and 1 is a convex combination of the endpoint, 1 and -1. But then, if this is true for a number in -1, 1, then this is also true for a vector in -1, 1 squared, because all you have to do is you look at your AB, and then you rewrite the a as 1 plus a over 2 times 1 comma b minus 1 minus a over 2 times minus 1 comma b, and then you do the same thing for the b times 1 1 plus 1 plus a over 2 times 1 minus b over 2 times 1 minus 1 plus blah blah blah, and you get the term that is minus 1 1 and the term that is minus 1 minus 1. So what's happening here, let me draw a picture, is whenever you have a square or product of interval in any dimension for that matter, any point inside that square can be written as a convex combination of the what we call the extreme points. So the points, minus 1, 1 here, 1, 1 there, minus 1, minus 1, and 1, 1. Now, this fact, you can keep adding dimensions to it, repeating the process, and what you have is that for a vector a1 until a d in minus 1, 1 to the d, you can always find a convex combination, so a sequence tj 1 to 2 to the d of elements that are between 0 and 0, 1 raised to the power 2d, that is such that, well, first of all, such that the sum of the tj is 1, it's a convex combination, and second of all, the vector a1 till ad can be rewritten as a convex combination j equal 1 to 2 to the d of the vector, let's write it like that, t1j till tj. So we can rewrite it as a vector of that form, where the set of vectors t1j till theta dj indexed by j equal 1 to 2 to the d really is equal to the set of all possible combinations of plus or minus 1s. So t1, okay, where so this set with 2 to the d elements is just an indexation of the set 1 minus 1 raised to the power d. It's a set of 2d elements that you can see as vectors of that form. All right, so this is the rewriting. So we've done it here with d equal 1, we've done it there with d equal 2. We're writing up the fact that every vector in minus 1, 1 to the power d can be written as a convex combination of the extreme points of that hypercube. So the points of the form a vector of coordinates that are either minus 1 or 1. Now, this is particularly helpful because this allows me to rewrite the mu n I had before as the sum L equal 1 to d indicator function of AL of n times AL. And what is AL? It is the sum j equal 1 to 2 to the d of the tj times theta L of j, because of what we have here. And note that the tj's are the same for every element of the vector, so for every L in that expression of mu n. So I have that, and now I'm gonna estimate the norm of the multiplier t mu. So not the multiplier TL that I'm really interested in, but the one with lambda replaced by mu. So what do I get for that one? So let's give ourselves a capital N and an x in x, and then let's look at the sum of mu n x en star en and truncate that at n. Okay, so what can I say about the norm of this? I can rewrite what mu n is using this convex combination argument that we had above. So we get a sum in L equal 1 to d, indicator function ALN, sum of the tj, theta L of j equal 1 to 2D, and then x en star en. Very good. Now, by triangle inequality, we can get the sum of the tj's out, and tj can also come out. It's just some number between 0 and 1 that only depends on j. And now we have the sum n0 to capital N of the sum L equal 1 to D of indicator function of ALN times theta L of J. Okay, that's my new coefficient. That's something that depends on N. And then x En star En. But now notice that this coefficient that depends on N, although it's a sum in L, there's only one element in that sum that is non-zero because the AL are disjoint. And the theta LJs are either +1 or -1. So this belongs to -1, 1. But in the lemma, we have proven that if you have a multiplier which multiplies by finitely many ones and infinitely many zeros, then such a multiplier is necessarily bounded with a norm that doesn't depend on the finite numbers of ones that you have. Now here, I don't have zeros or ones, I have -1 and 1, but this is the same thing, because if you have -1s or 1s, you can take that plus 1 and divide by 2, and this gives you something that is either 0 or 1, and you have only finitely many, at most d ones here. So you get that there exists a constant c by lemma 11.4 such that this holds, and c here is independent, of course, of n and x, and d of n, x, and d. Right, it's just the supremum, or really the c is well, maybe 1 plus the supremum of the norm of the pj's as bounded linear operators running over all finite subset of the natural numbers. So we've proven our theorem. We have proven our theorem because this sum of tj is equal to 1. So this is just c times the norm of this finite combination, linear combination of the En. So we've proven our theorem, but not for lambda n, but for mu n. So for an approximation of lambda n by a sequence that only takes finitely many values. So now we have to realize that we had given ourselves an epsilon and that our mu n is close enough to lambda n in L infinity norm, close enough in the sense of that epsilon. So let's do that final bit of argument and look at the sum of lambda n xn, sorry, not x, En star En, n equals 0 to capital N. Now, what have we got for that? Well, we can control it by c times norm of x for the c above, plus the sum of lambda n minus mu n times x En star En, just by triangle inequality. Okay. And now what can I say about this sum here? I can use triangle inequality pretty naively and control that by the sum n equals 0 to n of epsilon, and then I get the absolute value of x En star times the norm of En. Okay, well, maybe that's not quite what I want. That's a little bit too rough. So what I should do here is test that on a functional. So plus the supremum over all x star and capital in the unit sphere of the dual of the sum of lambda n minus mu n x En star, yeah, that's better, En x star. Okay, and now I need to control that term and show that I can make it arbitrarily small as I choose my epsilon arbitrarily small. So this term here, get still the supremum over x star in the unit sphere, and now I apply triangle inequality. I pick up an epsilon, and I have absolute value of x En star times En x star. This is an absolute value, but what I can do is the following. I can write this absolute value as x En star times En x star times the sine of x En star times En x star, right? And by sine of something, I mean +1 if it's positive, -1 if it's negative, and let's say +1 if it's 0, because it doesn't matter if it's equal to 0. It doesn't change anything in the sum. Okay, now that I have this sum here, right, I can see that as epsilon times the sup over the thing of the, what is it, the sum n equals 0 to capital N of, let's get the sign here, of sine x En star times En x star, that is some number which is equal to +1 or -1, times x En star times En, and then I'm taking the duality product of that with x star, right? That gives me exactly what I want. Okay, and now what can we do? Now we can just use the definition of the norm on the dual and control that by epsilon times the sup x star in Sx of x star of the sum n equals 0 to n of this sine En x star times x En star En. Okay, but our basis is unconditional. So if our basis is unconditional, we have that these quantities here have to, so this series here has to converge. What we get then is that, so they have to converge, and in particular, we have that these quantities are bounded. So actually, well, we've already shown that for choices of plus or -1, so not only do the series converge, but the corresponding projections are uniformly bounded. That's what we did in lemma 11.4. So this has to be controlled by a constant times x plus the same constant, which is just defined in terms of the supremum of the projections onto finite sets, epsilon times the supremum x star in Sx star of the norm of sum n equals 0 to capital N of x En star En. Yeah, but then that doesn't depend on x star anymore, and that is controlled by the norm of x. So what we get is C times 1 plus epsilon times the norm of x. And that is true for every epsilon, and we don't even need to send epsilon to 0 unless we want to optimize the constant, but we have just proven here that these quantities are bounded by a constant that does not depend on capital N or on capital X times the norm of x. And we have done that for any lambda n of norm less than 1. So in particular, we could do that for any lambda n which subnorm is exactly 1, and without loss of generality, that is enough, because you can divide lambda n by the subnorm of lambdas, and then the subnorm of lambda n divided by the subnorm will be exactly 1 anyway. So we've proven it here, if you want, with the times here the norm of lambda in an infinity, but we've normalized that to be 1. And this concludes the proof of the theorem, which shows that whenever you have an unconditional basis and you look at diagonal operators with respect to that basis, you know when these operators are bounded on the Banach space. They're bounded as soon as their entries on the diagonal form a bounded sequence lambda. Now this is very helpful. That means that we do understand the boundedness of diagonal operator with respect to unconditional basis just as well as we did when we were looking at operators acting on orthonormal basis of a Hilbert space, as in the spectral theorem, for instance. Now, this is all good and well, but we need to be sure that in Banach spaces that are not Hilbert spaces, we can find some appropriate unconditional basis. Now that will be the subject of the next video, where we will look at a concrete unconditional basis of LP that is valid for all p strictly between 1 and infinity. That's called the Haar basis.